Hello, welcome everyone. Let me introduce myself. My name is Shlomi Steinberg. I am a PhD student at the University of California, Santa Barbara. Today I will be doing this post-apocalyptic presentation of my paper, Accurate Rendering of Liquid Crystals and Inhomogeneous Optically Anisotropic Media. In the paper, I describe a technique to render liquid crystals. Liquid crystals are, incredibly useful and truly are a fascinating class of materials, a class known as optically anisotropic materials. This terminology implies that the optical properties admitted by such a material depend on the polarization and direction of the propagating light. Those materials, be it liquid crystals or any dielectric that is experiencing mechanical stress, a window or molded plastic, also tend to be highly inhomogeneous, meaning their optical properties change over space. All of this gives rise to a host of very unique optical phenomena and very interesting interference effects, and the point is that all of this also makes rendering such materials accurately remarkably difficult. In the paper, I show that the light transport in an inhomogeneous optical anisotropic material can be formulated as an operator-valued ordinary differential equation. This is actually also the case with any light transport problem that is expanded under some orthonormal basis, for example, spherical harmonics, and then expressed as an ordinary differential equation. So, today I'm actually not going to discuss the optics at all. The optics of these materials are really interesting and have been thoroughly formalized and discussed in the paper. You are more than welcome to check it out, please do so. What I would like to do today is actually present the technique itself in detail. In most generality, such an ordinary differential equation takes the following form, and that will be my starting point for today's presentation. The differentiation variable, which in this formulation is called z, can signify depth or distance from the source, etc., depending on the problem. The operator A is a linear operator that is an arbitrary, complex-valued square matrix, which can be a continuous function of z, that is, its known constant. The technique that I will be presenting is a general-purpose mathematical framework that is designed to generate an approximate but accurate analytic solution to such a light transport ODE. All right, let's consider again our starting problem, our starting point. For the problems I solve in the paper, which are liquid crystals, droplets, and shells, and inhomogeneous optically anisotropic slabs like crystal plates, a 2x2 matrix A is sufficient, and that is what I'm going to discuss first. Before we conclude, I will discuss how to extend the technique to other problems, including higher dimensional problems. The difficulties of the stated problem are, as expected, considerable. First, when expressing a problem in this form, we are usually interested in coherent or partially coherent light transport, which means we want to account for interference. However, that requires carrying phase information, which is very high frequency information, resulting in highly oscillatory ODE. This makes finding a good approximation a challenge. Second, we obviously are not expecting to find an exact closed-form solution. This will not be possible in general even for a typical scalar ODE. But to make things worse, unless the operator A commutes with itself, which is very rarely the case, for an operator-valued ODE, there does not even exist a finite representation of the solution, not even in form of an integral or any kind of finite representation. The best we can do is an infinite aggregation via a quite nasty series expansion of nested integrals. which again makes any analytic treatment hard. Okay, we call a matrix omega, highlighted in blue, the solution to the differential equation if the matrix exponential of omega, when acting upon the boundary conditions, produces the desired answer to the problem. Omega is then what we want to find. Those differential problems are the kind of problems that arise frequently in physics, of course, and indeed the expansion that I was talking about originated in physical literature, and it is known as the Magnus expansion. By itself, that expansion is, as mentioned, too complicated to be of much use. However, an immediate consequence of the Magnus expansion is that if I were to write out my linear operator A as a linear decomposition over some generators of some Lie algebra, that is, some matrices B subscript J, then I can represent the solution as a product of matrix exponentials as follows. If the generators, the matrices Bj, are known a priori, then the problem reduces to finding a set of scalar functions, which we denote f subscript j, and thus we have represented the solution as product of matrix exponentials, and you will see why in a moment. So to make progress, we are going to employ a somewhat involved algebraic construction presented by Way and Norman. Given a Lie algebra generated by a particular choice of our basis Bj, that is, a particular representation of the solution, as was just discussed, Way and Norman's construction will ultimately result in a differential system for those scalar functions f. That is, a system of scalar ordinary differential equations. And here comes a key step. Okay, our original ODE is on the left, and on the right we have the solution, omega in blue, and its representation as a product of matrix exponentials. Let's choose the following four-element basis in that particular order. Surprisingly, order does matter, very much so, because Way and Norman's construction is actually sensitive to the order of the basis. Change in order will produce an equivalent but different analytic representation for our scalar functions f. If you aim to perform numeric work, as is usually the case for physics, then it is generally of little consequence. However, if what we want is to make additional analytic progress and derive analytic representations, then those small changes matter a lot. Slight changes in basis choice, including order, are the difference between having and not having higher order differential terms or transcendental or trigonometric functions in the resulting differential system, all of which we very much would like to avoid, of course. Okay, so given that particular choice of basis, after a bit of algebra, see the paper, this is a system that is a solution that we get. So let's examine for a moment what we have accomplished so far. We started with an operator-valued ordinary differential equation with a 2x2 linear operator, that is, 4 degrees of freedom, and ended with the following system, which also admits 4 degrees of freedom. So those scalar ODEs are tamer beasts, so to speak, compared to their operator-valued counterparts. And do notice that the final two ODEs are separable. Therefore, 2 degrees of freedom have already been reduced to easier integration problems. We are left only with a linear scalar ODE and a more problematic quadratic Riccati ODE. If we were to solve those ODEs, we would be left with an exact solution to the original problem. And notice, we did not make any approximations nor assumed anything about the operator A. And That is because we can't really assume much. The original problem, as discussed, is widely oscillatory and misbehaving. So the natural question is, of course, are the equations for our scalar functions f as difficult, as unyielding? And the answer is an emphatic no. Why? Because the functions f are complex valued in general, therefore, in our representation of the solution as a product of matrix exponentials, we end up taking the exponent of complex values. And this is truly where, so to speak, the magic is. Not in reducing the original problem to a pair of scalar ODEs, which is good analytic progress, of course, but actually the real reason why we can now produce analytic accurate approximations is because that representation has abstracted away a very significant degree of nonlinearity. That is, those scalar functions f are immensely better behaved than the operator A. Let me show you. In the paper, I render quite a few materials, and to get a rough idea of the tractability, I used MATLAB's ODE solver to numerically compute solutions to one of the real problems. For the original problem, the operator valued ODE, numeric computation takes close to a day for some specific input on a new powerful desktop computer. That is, we render 1 pixel per day. For the equivalent formulation that we just derived, numeric computation on identical input, solver parameters, and hardware takes less than 10 seconds. And let me remind you, this is an exact solution. You can also compare the following graphs of the imaginary parts of one dimension of the solution on the left, and on the right against graphs of the imaginary parts of the functions f. A few seconds per frame is still way too much, so we do need to derive actual analytic approximations for those 4 scalar functions. In the paper, I do exactly that by approximating via finite sums of Gaussian integrals. Gaussian integrals, of course, do have a closed form solution, and thus all the results in the paper have been rendered at interactive performance. And nonetheless, those derivations of those approximations constitute a much simpler analysis, so to speak, and I believe they're less interesting. Furthermore, they are also somewhat problem-specific, so I won't be talking about that today. But again, please do see the paper for details. Instead, let me briefly present the rendering pipeline. Every rendering in the paper was done on the GPU at double precision to maintain numerical stability. First, all the discussed mathematics are done offline symbolically with the help of the MATLAB API. Closed form results are then written out, parsed, converted into C code, and fed through the GNU C compiler for optimization. A Gimbal plugin for the GNU C compiler then writes out the optimized code, the intermediary optimized representation, into a GLSL shader, which then can be fed to the GPU and used for rendering. So the optimization step is actually crucial, and the C compiler has been proven to be really the right tool for the job. The output from MATLAB can be massive. It can be hundreds of megabytes large, and worse, it can be highly numerically unstable. The optimization stage serves to eliminate easily 99.9% of the code, and being a more numerically aware optimizer, it also produces far better code. Likewise, it's also very easy to fine-tune how aggressive the optimization is, as needed. Finally, also because the integration has to be symbolic, it is very easy to encode user control variables into the shader in order to, for example, on the fly adjust material parameters, etc. Okay, so let's talk about how would we apply the same technique but to a different problem. As mentioned, this framework is applicable to anything that can be written as an operator-valued ODE. The hard part would be choosing the basis, and remember that order actually matters. This choice of basis is going to affect the complexity of the resulting differential system, and it's actually not the dimensionality of the problem, the size of your matrix, that is relevant, but how many degrees of freedom are introduced. And the more degrees of freedom you have, the more scalar differential equations you're going to have. If you have n basis elements, you're going to get n scalar differential equations. However, obviously, the difficulty of making further analytic progress has very little to do with just the size of the differential system, but of course with the ODEs themselves. Producing a good system will require some trial and error, due to the way the construction works, and choosing a basis such that the limit multiplication table is simple helps generate a simpler system. By a simple multiplication table, I mean that if you apply the Lie bracket to any pair of basis elements, you want to get, in general, another basis element, and not an intermediate result. And you want this to happen as often as possible, for as many pairs as possible. This is the primary trick. You can check that in my formulation, with the basis which we chose, if you apply the Lie bracket to any pair of elements, you will always get another element, and no intermediate results. This greatly helps to produce simple ODEs. Okay, let me conclude by demonstrating to you the actual accuracy of the presented framework. On the left, we have a microscopic photo of a liquid crystal shell viewed under crossed polarizers. And this was taken by Professor Lagerwald's team in the University of Luxembourg. And on the right is a rendered image of the same liquid crystal shell. More results, the paper, as well as additional information are all available on my website. Thank you very much for watching. Goodbye.